Native is made with 9 clean ingredients and is good for your skin without leaving white marks or residue.
Heavenly.
72-hour odor protection that cares for skin isn't a myth.
It's Native.
1 week only, we're offering our Game Dev TV Lifetime Membership, where you will get to own every single Game Dev TV course for life. That's every course we've made in the past and every course we will ever make in the future. In addition to owning every Game Dev TV course, you will gain access to an exclusive lifetime member Discord channel, special events, early access to courses, and bigger discounts for our other non-course products such as workshops or asset packs. We offer lifetime membership for only 1 week each year, and each year the price increases, meaning that the price will never again be as low as it is right now. So if you're serious about learning game development and
probably know Vistaprint for business cards. But did you know we print everything you need to brand your business? We print banners and signs that help you stand out, and must-have merch like tote bags, t-shirts, and hoodies. If you need it, we print it. Print it all with 20% off for new customers with code NEW20 at Vistaprint.ca.
Bank more encores when you switch to a Scotiabank banking package. Learn more at scotiabank.com/banking packages. Conditions apply. Scotiabank, you're richer than you think.
we should be good. Okay, so let's go ahead and compile this. Okay, so I have a successful compile. Let's head back in the editor, and here on Pawn Tank, of course we don't see anything, because Pawn Tank is derived from base pawn, and the components we just added, we added to the tank class. So BP Pawn Tank is not going to get those because it's not derived from the tank class. Now we could go and create a new blueprint based on the tank class, but then we'd have to set up these components all over again, and I don't really feel like going through all that work a second time. There's an easier way. We can reparent this blueprint to the tank class. We do that by going up to class settings, and in the details panel with class settings selected, we see class options, and there's this parent class. The dropdown shows that it's set to base pawn, but if we click on it, we can search for tank and choose tank as the base class. And now this blueprint is derived from the tank class. So we see that all of those properties we set with our components, such as the mesh and the capsule size, they're all still there, only now we see a camera. In fact, we have a spring arm and a camera, and if we select the spring arm, now we can see that red line. So this is great. So I could take this spring arm component and change its target arm length if I like. I could set it to something like 600. And I can even change its rotation so that it's angling the camera down at the tank by selecting rotation mode and rotating it up a bit, like so. Now I'd like to point out that you shouldn't change the camera's location. It might be tempting to select the camera and move it around in the world so that you position it and angle it just right. But this is not the correct way to do it. The correct way is to set the rotation and target arm length of the spring arm component. And the reason is you want that camera attached to the end of the spring arm. The spring arm has lots of different built-in features, such as shrinking in when the camera hits up against a wall to avoid obstacles blocking the view to the pawn, and other things like that. So you're going to want that camera attached to the end of the spring arm and then adjust the spring arm rather than adjusting the camera's position and rotation. So in this video, we created the tank class, and we derived from base pawn to inherit those qualities from the base pawn class. We added a spring arm component and a camera component and exposed those to the editor using visible only and put them in their own category. So we're getting closer to the finished product step by step, and we'll continue developing this tank in the next lecture. I'll see you soon. Welcome back. In this video, we're going to talk about possession. Now, we're not talking about demons infesting your body, we're talking about controlling pawns in the world. So let's talk about how we can designate a pawn to be possessed. So we're back here in the editor, and we have several pawns in the world. Now, by default, none of these are designated to be possessed by a controller. That means we cannot control them. If we press play, we'll see that we have the ability to move around with the WASD keys. That's because we are controlling the default pawn. This is something built into the engine, and it will be there for us if we do not designate one of our pawns to be possessed. Now, the way to designate a pawn to be possessed is to select the pawn instance in the world, and in the details panel, search for a variable called AutoPossessPlayer. Now, AutoPossessPlayer by default is set to disabled. But if you click the drop down, you'll see players 0 through 7. Now, these are not talking about multiple players in a networked multiplayer game. These would be multiple players on a single instance of the game, such as in a split-screen game where two people are playing on the same console or computer. So for our game, this will always be player 0. Now, what you do is you set this to player 0 for the pawn you would like to possess, and then when the game starts, that pawn will be the one possessed by player 0. And again, in our game, there is only one player, and that is player 0. So as a challenge, I'd like you to experiment with this possession thing. Set AutoPossessPlayer to player 0 on one of the turrets. See what happens. Press play and observe the results of setting this variable. Then then try setting it on the tank. Now, you're going to need auto possess player set to player 0 only on one of the pawns at a time. Otherwise, the engine doesn't know which one you mean to possess, so it's just going to pick one for you. So make sure auto possess player is disabled on all pawns except for one at a time. Pause the video and experiment with possession now. Okay, so the first thing I'm going to try is I'm going to select one of the pawn turret instances and set its auto-possess player to player 0. Now, if I hit play, I'll see that I'm stuck to this turret, and of course I can't move around or anything because we haven't programmed any movement, and we're not even going to for the turret anyway. So this is not very exciting. It's actually kind of frustrating because we're stuck to this turret and we can't move around. We just see the tank sitting there. So I'm going to hit stop, and with that same pawn selected, I'm going to change this auto possess player back to disabled. Now the next thing I'm going to do is select our tank. Now you may have noticed, as soon as you selected the tank in the world, we have a little pop-up window showing us the view from that tank's camera. Now this is a nice built-in feature because it's showing us the view that we would have from this camera if we were possessing the pawn. And we can see that if we set auto possess player to player 0 for the tank. Now let's go ahead and hit play and check it out. We see the view from the point of view of that camera. So that's pretty awesome. Now again, we can click in the viewport and try to move around, but we have not handled any input. We're not changing its location with anything in the code. That's something that we have to implement ourselves. But the possession part, actually controlling the pawn, that we are now accomplishing. So in summary, we learned how we can possess a pawn, and that by setting its auto-possess player variable to player 0 is the way to do this. So now that we're possessing the pawn, it's time to control and move the pawn, and that we will cover in the lectures to come. Exciting stuff. I'll see you soon. Hello and welcome back. Now we're ready to start handling user input. That means we'd like to press the keyboard keys and move the mouse and click the mouse and see our tank react to that input. Now in order to do that, we first need to actually get that input, and we're first going to start doing that using axis mappings. So let's talk about this. Now here in the project, let's go to Edit and Project Settings. And if we scroll down and select Input, then we see our bindings here. And under bindings, there are action mappings and axis mappings. We're first going to get into axis mappings. we're going to take a little bit of a deeper dive into what these do and how they work. So we have 3 of them. And if I click on the drop-down arrow, I'll see here W and S, and these are talking about the W and S keys on the keyboard. These are assigned to this particular axis mapping, which is called move forward. So let's discuss how this axis mapping works. So we saw in the Unreal Editor that we have this axis mapping called move forward, and it's got the W and S keys assigned to this axis mapping. So what does this mean exactly? Well, in Unreal Engine, we have something called an axis mapping. An axis mapping is something that's processed every single frame of the game. You assign keys to an W and S key. keys on the keyboard. And next to scale, there's a number, 1.0. And you may have noticed to take this function and now here's how it works. If we're not pressing the W or the S keys, this axis value has the value 0. So the move function that's bound to the move forward axis mapping is called every single frame, and the float value passed in is 0. Now let's say we're pressing the W key. The W key has its scale set to 1.0. This means that our axis value is going to be 1.0, and that's what gets passed into the move function. So every single frame, the move function is called with a value of 1.0 passed in. Now let's say instead we're pressing the S key, which has a scale value of negative 1.0. This means that every single frame, the move function will be called and negative 1.0 will be passed in. Now, in the case where we're pressing both W and S, then both of these values are added together. So we get the 1.0 from pressing the W key, and we get negative 1.0 from pressing the S key. Now these both cancel each other out, so if we're pressing both at the same time, the move function will be called with 0 passed in. So depending on which combination of keys we're pressing, we'll get a different value passed into our move function, and we can do whatever we like with that value, such as use it to move the pawn. We'll talk about actually moving the pawn soon enough. For now, let's just work on actually setting ourselves up so that we can handle this information from the axis mapping system. Okay, so now that we know how the axis mapping works, it's time to create a callback function that we can bind to the move forward axis mapping. So I'm going to close project settings and hop back into VS Code. So here in VS Code, we'd like to create a function that we can bind to the move forward axis mapping. So here in tank.h, we can create a private function. Now it's going to have the void return type, and I'd like to call this move. Now it needs to have a float input parameter, and we're going to call this value. So let's take our move function and define it here in tank.cpp. I'll stick it here just under the constructor, and we need a tank with the scope resolution operator before the function name. So we have this move function, and we're ready to bind it to our move forward axis mapping. And that is done inside of a function called setUpPlayerInput component. That should sound familiar. In fact, if we open our Explorer and go back to basepawn.h, we can scroll down and see in the public section the function setUpPlayerInput component. We'll see that this is an override of an inherited virtual function. Now, the basepawn class does not really need to set up any inputs, and that's what this function is for, handling input from a player. Now, our basepawn class doesn't need to handle input, but our tank class does. So what we can do is take this function out of basepawn.h, but I'm going to copy it because we need and I'd like to call this move. Now it needs to have a float input parameter, and we're going to call this value. So let's take our move function and define it here in tank.cpp. I'll stick it here just and we're going to call this value. So let's take our move function and define it here in tank.cpp. I'll stick it here just under the constructor, and we need a tank with the scope resolution operator before the function name. So we have this move function and go back to basepawn.h. We can scroll down and see in the public section the function setUpPlayerInput component. We'll see that this is an override of an inherited virtual function. Now, the basePawn class does not really need to set up any inputs, and that's what this function is for, handling input from a player. Now, our basePawn class doesn't need to handle input, but our tank class does. So what we can do is take this function out of basepawn.h, but I'm going to copy it because we need it in tank.h. So copying this function, I'm going to come over to tank.h, and here in the public section, I'm going to paste it. And since we don't need it in basepawn, I'm just going to remove it from the basepawn class. And in fact, I'm going to go into basepawn.cpp and remove it from here as well. So let's go ahead and delete setUpPlayerInput component from basepawn.cpp. And now it's no longer in the basepawn class. So let's go ahead and save our changes and close basepawn.h and cpp. And now we have setUpPlayerInput component declared in tank.h, but we also want to define it in tank.cpp. So here in tank.cpp, I'm going to add the definition just above the move function. So this is void, and it's a tank setUpPlayerInput component. Now let's go back to tank.h and see what its input parameter type is. You'll see that it's forward declared here inside the parentheses. This is something you can do if you want to forward declare a class type in a header file. So it's forward declared here, and we need this uInput component pointer type, and the parameter is called player input component. So we need this input parameter in tank.cpp. So in the parentheses for setUpPlayerInput component, we're going to have a uInput component, that's a pointer, and it's called PlayerInput component. So now the function signature matches that in the function declaration. Now back in the CPP file, let's give this function a function body. And we're overriding this function, and it's a good idea to call super setUpPlayerInput component. Now, since we're calling the parent version of setUpPlayerInput component, we have to pass in an input of type uInput component. We're going to pass in the input parameter to this function here. So this way, the parent class will call its version. Now, the base pawn tank is not implementing this function. We just removed it. But the parent class to base pawn will call its version. And whenever you override a virtual function like this, calling the super version is a good idea so we don't miss any functionality implemented in the parent version. So why are we doing this? What is setUpPlayerInput component good for? Well, one of the things it's good for is binding functions to axis mappings. We'd like to bind our move function to the move forward axis mapping, and we do that here. We do that using this input parameter player input component. That's what this object is designed for. We take the player input component, and on this pointer, we use the arrow operator to access a function called bindAxis. Now, bindAxis takes a few input parameters. The first is a string literal, which means we're going to use the text macro. Now, what do we put in the quotes? We put the name of the axis mapping. We saw in the editor that this axis mapping is called move forward. So we're choosing choosing that axis mapping to bind to. The second input parameter, this is going to be a pointer to the object we're binding the function for. This is a pointer to the instance of the particular class we're in. And since we're in the tank class, this will point to the instance of the tank pawn in the game. Now the third parameter is the address of the function we're binding. So we have a tank move. Very important that we need to fully qualify the function name with the name of the class. And right here in front of the function name, we need the address of operator. Now, if you're not familiar with doing something like this is simply taking the address of a function. Functions can have addresses just like variables can. So using the address of operator is a way to pass functions into other functions. So that's why we need that address of operator. So we have our function call to bind axis. Now you're probably noticing the IntelliSense error pointer to incomplete class type uInput component is not allowed. Now we know what can cause this. For one, it could mean that we need to include a header file. Another possibility is that it's a false error. You can easily find out By compiling. So let's attempt to compile. We'll see that we have a successful compile, so we know this is a false error. But again, if you want, you can add the include just to remove that so it's not bothering you. Now we know that the class type that it's complaining about is uInputComponent. So here's uInputComponent in the documentation, and here's the include. And if we add this up here at the top of the tank CPP file, we'll get rid of that pesky false error. And again, because these have the pragma once include guards, we know that inputComponent.h is not going to be included more than once. And there go the squigglies, they're gone. So now we know this move function will be called every frame, and value will have a particular float value, depending on whether we're pressing the W or S keys. Now, simply knowing that the move function is bound to move forward is not quite enough. As developers, it's nice to have some sort of confirmation that things are working. So what I'd like you to do as your challenge is to use uilog in the move function to print the value that's being passed into move, that float called value. So use %f in uilog to log the value of the float value to the output log, and then playtest the game and press those keys and see what you get printed out to the log. Pause the video and add this to the move function now. Okay, so here in the move function, I'm going to add a UE log. And this can be log temp, warning, and for the text macro, I'm simply going to put value, %f, and value. Now that's okay if you used a different verbosity or warning type. If you know how to do those things, that's totally fine. I'm just going to use a warning here. And I know you've used things like %s and formatted your log with a string value. %f, if you're not aware, is how you can format your UE log with a float value. So let's compile this. And back in the editor, I'm going to open up the output log and press play. Press the... We talked about axis mappings. Hello and welcome back. Now in this video, we're going to start talking about how we can move our tank. So to move the tank, we're going to have to add some sort of offset. And in Unreal Engine, when it comes to adding an offset, we need to make the decision whether to make the offset in local space versus world space. So let's discuss the difference between these two things. Now here in the editor, I have the pawn tank selected. And as soon as I have this selected, you'll notice that there is a gizmo. That's what this thing is called, a gizmo. It has 3 arrows and they're each a different color. Now, if you haven't noticed, at the bottom left of the screen is another smaller gizmo. And this sort of looks similar to the gizmo on the actor that we're selecting. So if I select any actor, we always get this gizmo. And of course the gizmo changes when we go from translate to rotate to scale mode. So as long as we're in translate, which we can access from this leftmost icon at the top right of the viewport or with the W key, we have the ability to move things or translate them by dragging on one of the arrows on the gizmo. And the colors correspond to the axes. Red is the x-axis, green is the y-axis, and blue is the z-axis. Now, if we rotate our view and look in a different direction, we'll see that that gizmo still points in the same original direction, and as we're rotating around, the gizmo at the bottom left of the viewport is rotating because the world direction does not change. So far, so good. Now, what we're looking at is world space directions. But for each actor in the world, there is a local direction, and we can see that by clicking on this icon that looks like a world. And the pop-up says, cycles the transformed gizmo coordinate systems between world and local space. When we see a world here, that means we're looking at world space. But if we click on it, it now turns into a cube, and we're now looking at local space for the given actor that we have selected. The gizmo at the bottom left of the viewport still shows us world space. But if I take this actor and I switch to rotation mode and rotate it, then when I go back to translation mode, you'll see that the gizmo is now pointing in a different direction. The actor itself has its own local x-axis. Green, local aligned with the world to see its direction. And this space versus, so the tank is pointing. Now, on the other hand, every frame that we want to move the tank. So we're going to be moving it in small increments, since calling a function every frame means we're calling it a lot. Now, for our tank, its own local x-axis is its forward direction. So this is the actor class. That's why it's called add actor local offset. Now, because it exists on the actor class, pawns will inherit this function, so we can use it. Now here's the syntax. It has 4 input parameters. The first is an F vector called delta location. So we're going to need to create an F vector that we can pass in to this add actor local offset function. So we know about this add actor local offset, and I'd like to experiment with this just to see how it works. So we can do this in the tick function. Now we are not overriding the tick function here in the tank class, but we do have it in the base pawn class. If we go to basepawn.cpp, here we have the tick function, and we're not doing anything here, and this is perfect to do some experimentation. So what I'm going to do is type add actor local offset, just like that, and I'm going to right click and select go to definition. Now here in the actor.cpp file, we have the definition for add actor local offset. Now notice something interesting. It's checking if root component is not null. And if it's not null, then it calls this function add local offset. So really what we're doing is adding an offset to the root component. And since all other components are attached to the root component, they'll move along with it. So it's important to note that when we're adding a local offset, we're moving the root component, and everything else just moves with it. Now, if we hover over add local offset, we'll see that all 4 of the input parameters are listed here. And aside from the first one, which is an f vector, the others have default values. Notice bool b sweep. It says equals false. The 3rd and 4th input parameters also have these default values. This means that if we call this function and do not pass in inputs for the last 3 input parameters, then they'll be set to these values by default. Now I'm going to close actor.cpp, and here in the base pawn tick function, I'd like to call add actor local offset each frame just to see how it works. Now, we know that the first input parameter is an f vector. It's called delta location. This is the amount of movement we would like to add each time we call this function. So I'm going to create an f vector called delta location. So f vector delta location. Now I'd like to zero out this vector. In other words, make sure that it's initialized with all zeros. Now I want a 0 vector. I can pass in 0.f, and x, y, and z will all get 0.f, so this will serve my purposes just fine. Now I'm going to take delta location.x, and I'm going to change that to 2.f. That way we have a vector with y and z set to 0 and x set to 2. So I'm going to go ahead and pass delta location into add actor local offset as a sort of experiment. Now I can get away with calling add actor local offset and just passing in the first input parameter, as the other 3 are optional. So I'm going to compile this and see what happens. Now if we go ahead and hit play, notice a couple of things. First of all, look, the tower is moving too. That's because we put this in the tick function for base pawn, and both of these pawns inherit from base pawn. So in fact, all of these pawns were moving. And the interesting thing is that they're all moving in their own x-axis directions. We can see everything move at once from this point of view if we click the drop down next to play and select simulate. This allows us to play the game without possessing any pawns. So if I click simulate, check this out. Every pawn is moving in its own x-axis direction. That is actually pretty weird and pretty cool. So this shows us how add actor local offset works. It moves things in their local directions. Now we can get out of simulate mode by clicking the drop down and selecting selected viewport, and this will allow us to play in the regular play mode. Alright, I'm going to stop this, and we can go back into base pawn, and we can remove this experimental code. I'm going to go ahead and just delete it out of the tick function. So we now know how add actor local offset works. So let's go back to tank.cpp, and here we have the move function. We know that this function is being called every single frame, and we know that value is equal to 1 if we're pressing the W key, and it's -1 if we're pressing the S key, and it's 0 if we're pressing both or neither. So for your challenge, you're going to move the tank using add actor local offset. So in the move function, you're going to create an f vector called delta location. Now make sure to zero out x, y, and z. You can do this in any number of ways, such as using one of the various f vector constructors. Now once you've zeroed out all the components, then set its x to the value of value, that float input parameter in the move function. Once you've done this, go ahead and call add actor local offset, passing in delta location. Pause the video and do this now. and I'm going to create an F vector called delta location. Now I can use one of the F vector constructors. I've already shown you how to create a new vector with all zeros. I'm going to show you another way, which is to initialize this with F vector 0 vector. And this is exactly what it sounds like, a vector with 0 for each component. This is just to show you an alternative way. So we have a 0 vector. Now I'm going to take delta location.x and set that equal to value. And finally, I can call add actor local offset, passing in delta location. So let's compile this. And back here in the editor, I'm going to take my tank and I'm just going to orient it so that it's facing the world X direction. And then I can hit play. And now clicking in the viewport, if I press the W key, I'm moving forward. And if let's compile this. And back here in the editor, I'm going to take my tank and I'm just going to orient it so that it's facing the world X direction. And then I can hit play. And now clicking in the viewport, if I press the W key, I'm moving forward. And if I press the S key, I'm moving back. If I press both, they cancel each other out and I'm not moving at all. And of course, if I don't press anything, I don't move either. So we now have movement for our tank, but it's a little slow, so we're going to have to do some adjusting, and we're also going to talk about fine-tuning this movement mechanic with our tank. So in summary, we learned about add actor local offset and the difference between world space and local space. In the next video, we're going to continue perfecting this movement mechanic with our tank. I'll see you soon. Hello and welcome back. In this video, we're going to talk about how we can speed up our tank. We'd like to control exactly how fast our tank is moving, and right now we're just passing in this delta location vector into add actor local offset, and we have no control over how fast the tank is moving. It's actually moving quite slow. So we're going to make a speed variable that we can use to control that speed, and we're also going to take into account the frame rate of our game. As our game is changing frame rate from frame to frame, we actually are not getting consistent movement. So to take that frame rate into account, we're going to talk about something called delta time. So we're here in the editor, and if I hit play and I start moving the tank around, it's not something you can really notice necessarily, but our tank is not moving in a consistent rate from frame to frame. If I click that, per second, you might have missed it, but the frame rate went down and then came back up because during that beginning stage of the game, lots of things were happening. All of the actors were calling their begin play functions, and there's some behind the scenes setup for the world. Now, if I start playing the game, that 120 FPS that I'm getting is changing from frame to frame, even though it hovers around 120. So the reason this causes inconsistent movement is because as the frame rate goes down, those tick updates are being called less often. And if we're moving this tank by the same amount each frame, then and when the game gets delta time. So what's this mysterious function take up more factor local offset more often, then we're going to see our pawn moving faster. And it won't have a consistent pawn by, say, 10 centimeters per second time, meaning it's simply scale our tiny amount since tick value times delta time, meaning we'd like to scale value by delta time. Now, once we do this, we're going to make value very small because delta time itself is a very small value, especially if your frame rate is very high. So we're also going to need to scale this by something else, a sort of speed variable. And we can decide what this value should be in order to control the tank's speed. So we have a little bit of pseudocode here to guide us, and we now just need to implement this by creating a value for speed and finding out how we can get this delta time value. So let's talk about how we can access delta time from the move function. Now, Unreal Engine has multiple ways to get a hold of delta time. In fact, if you look at the tick function that we have in base pawn, delta time is a float input parameter. So if we're working in the tick function, we already have access to delta time. But in tank.cpp, our move function does not have that input parameter. But Unreal Engine has its ways. One way is to access a function called getWorldDeltaSeconds, which exists in a class called uGameplayStatics. As the name suggests, uGameplayStatics has lots of static functions that assist in programming gameplay. GetWorldDeltaSeconds returns delta time. Now, it has an input parameter here. It takes a world context object. You'll see this a lot in Unreal Engine. A lot of static functions will require a world context object. The world is an object of type uWorld. It's the top-level object of our game. It represents our map, which contains all of the associated objects in our game. Now, static functions, such as getWorldDeltaSeconds, have no idea which world we're in. We need to tell this function which world we're in so it can access that world and get that delta time value. Now, in order to tell it which world we're in, we can pass in a pointer to an object that exists in that world. While we're working in the tank class, we can pass in the keyword this. This is a keyword that we can use inside of any class in C++. What the this keyword is a pointer to the instance of any particular object that we're working in. So if we're working in the tank class, this is a pointer to the tank that we're in. So functions that require a world context object can often receive this as the input parameter because the tank we're working in exists in the correct world. So getWorldDeltaSeconds will know which world it's in and can retrieve us the appropriate delta time for that world. So if we're calling getWorldDeltaSeconds from within the pawn class, we're going to pass this in as the world context object. So you now have all the tools you need to control the tank's speed. So what you're going to do is create a speed variable, make this a float, and put it in a private section in the tank class. Now expose this to blueprints so we can adjust it as we're developing, which means you're going to give it a uProperty and use the appropriate uProperty specifiers that correspond to the level of exposure you would like. Now in the move function, we have that bit of pseudocode that we placed in as a comment, so use that as a guide. You're going to take the delta location f vector and scale its x by delta time. We just saw how we can access delta time using uGameplayStatics. And you're also going to scale x by the speed variable. Now because we're using a function in GameplayStatics, you're going to need to include the header file for GameplayStatics. Now I've shown you multiple times how I find the include for a particular class using the Unreal Engine documentation. So I'm going to challenge you to search for uGameplayStatics in the Unreal Engine documentation and find that header file. And if you can't find it, then just find the link in the resources for
You
this
probably
video,
know Vistaprint for
control
business
a
cards,
speed
but did you know we
variable.
print
Now
everything
back
you
in
need to brand your
tank.h
business?
called
We print banners and
speed
signs that help
to
you
the
stand
base
out,
pawn
and
class.
must-have merch like
Now,
tote
I don't
bags,
need the
t-shirts,
speed
and hoodies.
variable here in
If you
base
need it,
pawn.
we print it.
This was
Print
just
it all with
practice,
20% off for new
so
customers
I don't
with
really
code
need it
NEW20
here.
at
In
vistaprint.ca.
fact, remember that I'm going to go ahead and delete those nodes. And compile and save my BP pawn tank. Okay, after cleaning up all that, I'm going back into tank.h to add my speed variable. And this is going to be in the private section here. I'm going to add it just above the move function, and it's going to be a float called speed. Now, I'm going to give it an initial value here. I think I'll try 200.f and see how that works. But since I'd like to be able to edit this in the editor as I'm developing, it's going to get a uProperty macro. And I'd like to be able to edit this on instances and on the default, so I'm going to make it edit anywhere. Now, you didn't have to do this, but I'm giving it a category. I'll create a new category called movement. Now, exposing it to the event graph is optional. I'm going to hold off on that because I don't think I'll need to access it in the event graph. If I need to in the future, I can expose it with blueprint read write or blueprint read only and use that meta allow private access specifier, but for now, I'm not going to. So I have a speed variable, and here in tank.cpp, I'm going to take value and scale it by speed. Now the last thing to do is scale value by delta time, which means I need uGameplay statics. So here's Unreal Engine's documentation. I'm going to go ahead and search for uGameplay statics, and here it is, uGameplay statics. So I just need to scroll down to the include line and copy this, and back in tank.cpp, I can paste it in. Now that I have access to uGameplay statics, I can get delta time. So I'm going to multiply by uGameplay statics, get world delta seconds. And as we saw, this needs a world context object. You can even see with the pop-up, it's asking for a world context object. So I'm going to pass in this. So now that I'm setting delta locations x to value times speed times delta time, I'm going to compile this. So we have a successful compile. So back here in the editor, I can go into BP pawn tank, and there's my speed right there. And if I select the instance of the tank in the world, I can search in the details panel for movement, and there's the speed, and I can set it to any value I like. If I crank this up and hit play, then I'm moving quite a bit faster. So this is the advantage of exposing the variable to blueprints. I can experiment and find a good speed that works for me. All right, so that's looking great. I'm going to go ahead and stop showing the FPS now. And now we have our speed variable, and we can change it, and that change will be reflected in the movement of my pawn. So we're now controlling the movement speed of our tank, and we have a nice speed variable that we expose to blueprints, and we can set that as we're developing and experiment with its value. We also learned about delta time and why it's important to scale our movement by delta time so it's frame rate independent. As the frame rate changes, we'll still get smooth, consistent movement with our tank. So looking back at our section plan, we're almost done with our first bullet point. We've created a tank and it can move throughout the world. Our second point is to handle input with WASD keyboard movement and mouse input as well. We've got that W and S part down, but we still need to be able to use the A and D keys, and we're going to use those to rotate the tank. So we're making good progress. In the videos to come, we'll work on finishing our ability to move the tank. I'll see you soon. Hello and welcome back. Now we are moving our tank forward and backward, but we have no way to actually steer the tank. So in this video, we're going to work on actually turning the tank using something called local rotation. This is the rotational analog to add actor local offset. Now add actor local offset had multiple input parameters, and we only passed in the first one as the other three were optional. but one of those other three had to do with sweeping. And we're going to discuss a little bit about sweeping before we continue implementing rotation. So I'm back in the documentation for add actor local offset. So let's take a look at these input parameters once more. The second one is called bSweep, and it's a Boolean. Now, if we scroll down a little bit more and read the information here for bSweep, it says whether we sweep to the destination location, triggering overlaps along the way and stopping short of the target if blocked by something. It also goes on to say that only the root component is swept and checked for blocking collision. Child components move without sweeping. If collision is off, this has no effect. So let's talk about what this means. Now, in games programming, sweeping is a technique done by the engine as long as sweeping is enabled. If we have a moving object, such as a sphere represented by this circle, each frame, as this sphere is moving, the engine is performing sweep checks. This means it's checking to see if that move for this particular frame would have resulted in an overlap between two objects. So I have this block here represented by this rectangle. Now let's just consider that these are the only two objects in the world. So while sweeping is enabled, as the sphere is moving towards the object, the engine is checking to see if these two objects are overlapping. Now, as the sphere continues to move, let's say during one of these frames, the sphere would have moved such that it's overlapping the other object. Now, what sweeping enabled does is the engine will detect this overlap and move that sphere back for that particular frame so that it never actually penetrates the object. Now, we never actually see the sphere penetrate the object. The engine catches that overlap before the movement is actually implemented, so the result is that we see that the sphere stops just short of overlapping. So if this rectangle were a wall, for example, the sphere would stop at the surface of the wall. That is what sweeping achieves for us. Now the document, here's our call to add actor local offset, and we attempt to move through a wall, for example, we'll see that we move right through the wall. So something isn't quite working here. Now let's look at what that root component for the BP Pawn Tank is. Recall we used the capsule component for the root. So with capsule component selected, in BP Pawn Tank, let's go to the Details panel and scroll down, and we'll see here a section called Collision, and here we see Collision Presets. And it has a drop-down, so let's expand that. Now, collision presets can be set to any number of options, and by default, we see Overlap All Dynamic. Now, depending on the version of Unreal Engine you're using, you may see something else here, but we can change this. If we select the drop-down and choose block all dynamic, then the grayed out options below change. Remember, we were on overlap all dynamic, and here we see 3 columns of checkboxes. These are collision responses, and the column to the left show a list of collision object types. So any given component has its own collision object type. Notice we can see the object type for the capsule set to world dynamic. And when we changed collision presets to block all dynamic, you'll see that the collision responses are all checked to block in response to all other collision. Now, if I move the tank so that we can attempt to overlap with the wall and sort of go around the other pawns, now if I press play, I block the wall as well. So this collision preset block all dynamic sets the collision response to block all other object types, and you can always see the collision. an object type of a particular component by selecting it in the Components panel and scrolling down to the Collision section in the Details panel and opening the drop-down for collision presets. I have the base mesh selected and its object type is World Dynamic and it's set to block all. So now we see that sweeping is working since we set our collision presets for the capsule comp to block all dynamic. And we saw in the documentation that only the root component is swept and checked for blocking collision. So it doesn't really matter what the other components are set to. We're only checking to see if the root component is blocking something. Now, one issue that's tripped up some here. So let's compile. This and see the effect of enabling sweeping. Now, if we press play and we attempt to move through a wall, for example, we'll see that we move right through the wall, the root. So with capsule components selected in BP Pawn Tank, let's go to the Details panel and scroll down, and we'll see here a section called Collision, and here we see Collision Presets, and it has a drop-down. Select the drop object type, the collision short of overlapping with the other pawns. Now, if I move the tank so that we can attempt to overlap